Okay, so this is a quick sound check. All right, so the signal shows pretty healthy. Let me see. Let's do this. All right, if anyone's watching, do me a favor. If the signal is cutting out too much, just do mention it in the Discord channel. I have the Discord app open, so I'll see it. I don't know if I'll actually be able to fix it on the spot, but I'll give it a shot. All right, so this is a quick linear algebra stream. And last time we started with this book by Paul Halmos, The Finite Dimensional Vector Spaces, and we ended on problem 3, where hopefully I gave you intuition on how to go about proving this problem. And the problem said to show that this set defined Z subscript M is a field if and only if M is prime. And we remember that this was, of course, the set of numbers from 0 to M minus 1, and the operations were we add the two numbers and we take modulo M. And the multiplication was multiply any two members of this set and take modulo M. And I gave you intuition as to why this set is a field if and only if M is a prime. Okay? Now, number 4 is the problem I want to stream right now. I was at work and I took a look at this problem and it was kind of interesting. And I actually like it a lot. So I want to go ahead and try and explain the intuition behind this. So here's the problem. The example of Z subscript P, where P is prime, shows that not quite all the laws of elementary arithmetic hold in fields. Okay? In Z2, for instance, 1 plus 1 is 0. So how does that work? Z2, Z subscript 2, what are the members of Z2? So Z2, Z subscript 2, is the set containing 0 and 1. And what are the operations? Well, the plus in Z2 says, of course, add two numbers. Okay? And then do mod 2. Right? So if I take 0 plus 0, and do mod 2, I of course get 0, right? So mod 2, that gives me 0. If I take 0 plus 1, mod 2, that gives me 1. But if I take 1 plus 1, well, 1 plus 1 is what? That's 2. But what is 2 modulo 2? What is the remainder after I divide 2 by 2? Well, there is no remainder, right? So I get 0. So even though in the regular algebra that is defined on the integers, okay, on all of the integers that we work with in elementary, in like K-12, 1 plus 1 equals 2. In this set, in this field, 1 plus 1 is not 2. There is no 2 in this field. 1 plus 1 is 0. It's the additive identity. Okay, so that's Z subscript 2, and that's what Paul Halmos says that, you know, not by this line he means right here, not quite all the laws of elementary arithmetic hold in fields. So this law is pretty strange, as we saw, where 1 plus 1 actually equals 0. Okay, so what is the problem here? Prove that if F is a field, okay, so we're given that F is a field, then either the result of repeatedly adding 1 to itself is always different from 0, or else the first time that it is equal to 0 occurs when the number of summends is a prime. So what is this saying? This says that if F is a field and I take 1, the multiplicative identity in that field, and I start adding it to itself, either I will never get to the 0, to the additive identity in that field, or else the number of times it takes me to add 1 to itself to reach the 0 will be a prime number. So in Z2, for instance, right here, how many times did I have to add 1 to itself to get 0? Twice. 2 is prime. Okay? So how do we go about proving this? Well, again, I'm not going to formally prove this for you. If you find this problem interesting, you should definitely give it a shot yourself, but here's the intuition. So, and Paul Halmos, by the way, in the beginning of the book, he does mention that unless otherwise specified, this addition and multiplication is the regular addition that we know. Okay. Now I'm gonna try and give you the intuition for the regular addition and multiplication that we know of. Okay, I haven't tried to prove this for the general case of any two operations that make f into a field, but you're welcome to give it a shot and see if that's true. I remember when I was in college, I remember that all finite fields were in a way isomorphic to z subscript or f subscript p. All finite fields were f subscript p. And so if that's true, then this theorem can be generalized. But I can't vouch for that. I haven't done that stuff in a long time. You're welcome to give it a shot. I'm going to try and give you the intuition for the regular addition and multiplication operations that we're familiar with. So suppose we have f. F is a field. F is a field with the regular addition and multiplication. Okay. Now, suppose I take 1 and I start adding it to itself. Okay, many times, suppose. And let's say the result is 0. All right, now, in the regular multiplication and addition, so adding 1 to itself like this is just the scalar multiple of 1, right? That's n times 1. N times 1. Now, this n times 1 gives me 0, right? That's what we're assuming. We're assuming I've added a bunch of 1s and I've gotten 0. How many 1s is that? That's n 1s. Okay, I've added n1, so I have n 1s and the result is 0. Now, remember that f is a field and n comes from a field and 1 comes from a field. Okay, now this is a product of two elements of a field that gives me 0. We know that in a field, when two elements multiply and give us 0, either one of the so one of those elements has to be 0, the additive identity of that field. So 1 is definitely not the 0, so it has to be n. N has to be the 0. Okay, now what is n? N is the number of 1s I've added to each other. It is definitely bigger than 0, right? There's more than 0 1s that we've added. That's what we're supposing. So somehow n is a number that is the additive identity in my field, but it's not the regular sort of the 0, the regular additive identity in the integers, right? N is some number that is the 0 of this field here. It's not the 0 of the regular integers that we know. Again, because n counts the number of 1s I have here, and we're assuming that we actually have 1s. It's not 0. Okay. Now I'm going to say, okay, suppose n is not prime. Suppose n is not prime. Suppose n not prime. So if n is not prime, then it is a product of two non-zero numbers, both of which are smaller than n. Both of which are smaller than n, right? So n is a product of two numbers, two positive integers, both of which are smaller than n. These two, a and b, are also coming from this field f. So we're back in the situation here where we're multiplying two non-zero numbers. We know they're both non-zero, right? Because that's what the definition of a prime is. The definition of a prime, the definition of a composite number is that it is a multiple of two non-zero positive integers. So neither of these a and b are integers, but they multiply to 0. This is a contradiction. We know in a field, if two numbers multiply and give me 0, one of them has to be 0. Okay, well, if n is composite, then neither a nor b are 0, but they multiply to 0, which is not possible in a field. Contradiction, which tells us that n has to be prime. Okay, so again, let's go over this one more time. You know, as I'm describing this, I realize that there are a lot of blanks to fill in. this is what I'm streaming here is not full proofs. I'm more so explaining this to myself. I'm trying to teach this to myself, really, and I'm trying to intuitively understand these things. So if you want to formally prove this, I strongly suggest you go through the proof yourself. But let's review what we just did. We have a field f with addition and multiplication. Okay, with regular addition and multiplication. Now, so what we were asked to prove is that if I'm adding ones to each other some number of times, then the result either will never be 0, the additive identity in that field, or the number of ones I have to add to each other is prime to reach 0. Okay, so I said, all right, let's suppose I have some number of ones that I'm adding and the result is 0. Well, how many ones am I adding? N ones. That's n times 1, right? N ones I have here. And I know the result is 0. Now I know that n is not the 0 from the integers, right? It is definitely a natural number. It's 1 or bigger. Why is that? Well, because I suppose that we have actually ones that we're adding to each other. So n is definitely bigger than 0. Now we're in a field. We know that when we multiply two numbers in a field and the result is 0, one of those numbers has to be the 0. It has to be additive identity. 1 isn't it, so it has to be n. So whatever this n is, whatever number this is, 4, 5, 10, 11, whatever, in this field, it is the 0. Like in Z2, number 2 is the 0. Right? In Z subscript 2, when we're looking at numbers modulo 2, 2 is our 0, as we saw here. In this field, the general n is our 0. Next, I said, okay, let's suppose n is not prime. Well, if n is not prime, then it's composite. It's composite, and it is a product. It is a product of two integers smaller than n. Two positive integers smaller than n. But the result of this product is 0, and we know that in a field that's not possible. We cannot multiply two non-zero integers, or two non-zero elements of any field, really, and get a 0. Okay? Hence, we have a contradiction, and n has to be prime. Okay. Now, do fill in the blanks, and I'm sure you'll have, here's one question, for example, I could ask. All right, so we suppose that n is not prime, it's a composite. Sure, it has to be a product of a and b. Well, who's to say a and b have to be in this field, right? Do a and b have to be in this field f? Is it possible that they're not there? Okay, so do try to prove these yourselves and ask questions. If you have any, it's a really awesome problem. Try to write the whole proof, and I'll talk to you later. Bye-bye.